This is a stress pattern of a ruler. The polymer making up the ruler has different stress points, mainly high and low stress points. And these stress points and these stresses depend on how uniformly the polymer is seized to make the scale or the ruler. And it is these stress points and these stresses within the materials which we are able to see on the surface of this scale through these amazing band of colors. These band of colors actually show us the different stress points and the different stresses. We can not only see these stresses in a ruler but also in something like a sellotape, which is also a transparent polymer. You can also see as to how the color of the tape changes when I stretch and pull apart the tape. This is because when I'm stretching it, I'm changing the stress pattern. I'm changing those high and low stress points, which gives a different color to the tape. This phenomena of seeing stresses within materials through this amazing band of spectrum is known as birefringence. And that is the topic of this very video. So, in order to understand birefringence, we first need to understand polarization. So, we all know that light is an electromagnetic field. It's a mixture of oscillating electric and magnetic fields which are perpendicular to each other. These electric and magnetic fields oscillate along the y and the z axis. And we can also calculate as well as find out the direction of the energy transferred by these electromagnetic fields using something called a Poynting's vector. Now, an electromagnetic field or light can be represented through some equations known as Maxwell's equation. And the math within these equations proves the existence of polarization. Now, the math tells us that it is possible for the existence of those electromagnetic fields which have a different geometry as compared to the original one. So, for example, in this animation of an electromagnetic field, you can see that how the electric component is polarized vertically. It oscillates in a vertical direction. So we can call this particular electromagnetic radiation as a vertically polarized light. Now, in another animation like this one, the electric component or the electric field is actually polarized horizontally. It is oscillating horizontally. So we can say that this particular light is a horizontally polarized light. So depending upon the angle with respect to the horizon at which the electric component is oscillating, we can have different polarized light. So that exactly is polarization. It is a geometric oscillation of electromagnetic fields. So now let's understand what are these things. So this is a polarizing filter, and it is a lot similar to those polarized sunglasses which you might wear on a hot sunny day. A polarizing filter like this one is made up of calcite crystals which are embedded in these two sheets. And I actually used this polarizing filter to show you the phenomena of birefringence. I had placed one of these polarizers on in front of my camera, and then I showed you the stress patterns within different polymers. So what a polarizer does, what this polarizing filter does, is that it only allows a particular polarized light to pass through it. So light sources like LEDs or halogen bulbs produce electromagnetic radiations which have different polarizations. So we have linearly polarized, horizontally polarized, circularly polarized, and even unpolarized light being emitted. So now if I take my polarizing filter and if I keep it in this horizontal direction, then this particular filter will only allow horizontally polarized light to pass through it. It will only allow that particular electromagnetic radiation which has its electric component oscillating horizontally. And I can change the polarization of the light being passed through this filter by changing the angle as well as the direction. So for example, if I shift this polarizing filter 90 degrees such that this is now aligned vertically, so this filter will only allow vertically polarized light to pass through it, which has its electric component oscillating vertically. So that is basically how a polarizing filter functions. That is the basic principle. And it also answers the question as to why there is no light when I keep these polarizing filters perpendicular to each other. So like right now all the light is being blocked, but the moment I change the angle, the light passes through. Why? So in order to answer this observation, let's imagine we have a polarizing filter which allows vertically polarized light to pass through it. Now if we take another polarizer and if we keep it behind the original one, behind the first one, in the same angle, in the same direction, then we won't see much difference. I mean, the same intensity of light passes through it. However, the changes only come when we change the angle. And that's happening because you see, this is allowing vertically polarized light to pass through it. But when I change this angle so that it is 90 degrees, so this will allow horizontally polarized light to pass through it. But since only vertically polarized light is being passed through it, there is no horizontally polarized light to pass through it. Thus, all the light gets blocked. From this direction or from this direction, every light, every single photon will get blocked because they allow different polarized light to pass through them, which have different polarization of the electric component. So, there is no light. So now let's come to the final piece of the quest and understand the mechanism behind birefringence as well as stress points. So the phenomena of birefringence normally asks for two of these polarizing filters. However, in my case, I only used one because I am using a liquid crystal display. A liquid crystal display is often used to produce laptop as well as TV screens, and the liquid crystal display itself has its own polarizing filter. So the light coming from these displays is polarized itself in a particular direction, and we can also find out the direction of the polarization of the light being emitted from the liquid crystal display by using a second polarizer and placing it such that the second polarizer does not allow the light to pass through it, because then the direction of the polarized light being emitted from the screen will just be opposite to the angle as well as the direction to which the second polarizer is orientated and does not allows the light or the photons to pass through it. The polymer making up the ruler, sellotape, and even smartwatch covers are made up of certain molecules, and these molecules interact with electromagnetic radiation in a very special way, such that when light or EMFs fall on these molecules rotate and bend and curve the electromagnetic radiations around them, such that the light undergoes two main changes. First of all, the polarization of the light changes, and also, since the molecules bend the light around them, the electromagnetic radiation undergoes overlapping and they overlap each other. However, even though they undergo overlapping, since they are of different polarizations, they do not interfere with each other. And that is why when we use only one polarizer to see these different polymers, we do not see a stress pattern and we do not see the wide range of colors. The magic of birefringence only occurs when we bring in the second polarizing filter. Because when we bring in the second polarizing filter, all those electromagnetic fields which were earlier unpolarized will now get polarized. So as we saw that when we had only one polarizing filter, the molecules within the polymer bend the light so that all the electromagnetic radiation had different polarizations. But when we bring in the second polarizer and when we place it in front of it, so all those different electromagnetic radiations get polarized in one particular direction. And because of that, we are able to see the interference of those electromagnetic fields with each other, due to which we are able to see these different colors. And we are able to see these different colors on the surface of the polymer because of something called destructive interference. So when the light is being bent by these different polymers, these light waves undergo destructive interference as the crest and the troughs of these electromagnetic radiation cancel each other out, such that these two light waves are completely out of phase. This limits the amount of longer wavelength, shorter frequency electromagnetic radiation to be emitted from that particular polymer, due to which the light which is being emitted is shifted much more towards the blue end of the spectrum, where we have shorter wavelength and high frequency electromagnetic radiations. So those areas which have high density of the polymer tend to have much more destructive interference, due to which they produce much more shorter wavelengths of light as compared to those areas which are much flattened out and produce longer wavelengths of light. So it is the destructive interference which actually explains everything, from the different colors with respect to different stress points, as well as the stress pattern within different materials. And what you might be surprised to know is that this technique is not only just used for, instrumental purposes, but it's also used by engineers so that they can also find out the stress patterns of different materials, and they can alternate their scientific equipments according to those stress patterns. So yeah, that's it for this video, and I hope you learned something new, you enjoyed this video. Thanks for watching, and I'll see you in the next one.